Hey, today we will finally see what structure on THH and more generally Hochschild homology in an arbitrary symmetric monoidal infinity category corresponds to the con operator that we saw appear on ordinary Hochschild homology. This is an action by the circle S1 considered as a group. And so we will see today what this means, having a topological group act on an object in an infinity category. And we will see how this action arises via so-called cyclic objects, first defined by con. I'm Achim Krause from Mathematics Münster. So in order to talk about the circle action on THH, we will first need to define what group actions in general are in the infinity categorical setting. So if you think about what a group action on just an ordinary object in a one category is, then you're assigning to every element of your group an automorphism of your object in a way that's compatible with composition and the group structure. So one way to encode all of this is that a group action on an object in a one category is simply given by a functor. So a group action on an object of a one category C is simply a functor from a category I'm calling BG to C. And what is BG? Well, BG is simply the category with a single object which has endomorphisms given by the set G. All right, and completely analogously, we can define a G action for just a usual group G in an infinity category. So a G action on an object in an infinity category by saying that we just look at functors from BG, from the nerve of this BG to C. And just as in here, you can recover the underlying object your group acts on by looking at what your functor sends the base point of this nerve of BG to in C. And what is this nerve of BG? Well, since BG was a groupoid, this is a Kahn complex. And it's a Kahn complex with just one single homotopy group. Pi1 is given by G. All the other homotopy groups are trivial. It's connected and the higher homotopy groups vanish. So this is a Kahn complex with loops. It's a connected pointed Kahn complex with loops simply equivalent to the set G. And there was this nice recognition principle for E1 algebras that tells you that you can recover a group like E1 algebra in the category of spaces by a de-looping. So every group like E1 algebra is simply loops of something, and that's a functorial correspondence. So one way to think about this nerve of BG is it's the space you get from this group like E1 algebra, G. And conveniently, the functor that exhibits that equivalence, so this inverse functor to omega in this context, is also called B. So a kind of overloaded way of saying this is that this nerve of BG space coincides with BG where B is the equivalence from group-like E1 algebras in spaces to connected pointed spaces. The inverse of a loop. So this is a little overloading, of course. So we will just drop the nerve at this point and just call this object BG. And in fact, it's, I guess, this context, this space, it's also called a classifying space of G, that motivated this, calling this one category BG over here. So maybe this overload, the overloading is the fault of this guy, but it's no problem since this is just a one category and it corresponds to that space. And one example for the kinds of spaces you can get here is you take the group Z, then BZ is weakly equivalent, is homotopy equivalent to the space S1. So giving a Z action on an object is the same as giving a functor out of S1 in your category. That's nice. So in general, right, this makes sense for any group like E1 algebra and not just a discrete group. So we can now define for any group like E1 algebra, G in spaces, and an infinity category C, we define the category of objects of C with G action as simply factors from this Kahn complex BG into C. Right, so the takeaway is you can not only make sense for having like a discrete group act on an object in an infinity category, but in fact any E1 algebra, any group like E1 algebra in spaces. And of course examples for E1 algebras in spaces you do get from, for example, simplicial groups or topological groups by taking their singular set. So for example, you can talk about having a Lie group act on objects of an infinity category. And that's what we're going to do. So the circle action refers to an action by the group S1. All right. And among other things, one thing you can do, of course, if you have a functor out of a category, is you can take its limit and co-limit. And the significance of this is that you should think of taking the co-limit of such an action, of such a functor, as sort of taking the underlying object, i.e. the value at the base point of BG, and sort of modding out the action, quotienting by the action, trivializing the action in a kind of homotopy coherent way. And so we call this co-limit homotopy orbits. So this is the co-limit of BG over BG of such an object with G action. So technically this is a functor from BG to C. We'll often use sort of the notation in an interchangeable way and not distinguish too much between such a functor and its underlying object. So you can also think of this as a space with some extra structure. So this colimit is called homotopy orbits, and similarly there's also the notion of homotopy fixed points, which you get by taking a limit. And as sort of a special case, in the category of spaces, we can look at a space X, and if we endow it with the trivial G action, which means that we turn the space into the constant factor from BG to spaces, then the homotopy orbits on my space are actually just the space X cross the space Orkan complex BG. And similarly, the homotopy fixed points are actually just the mapping space from BG into X. So these are pretty useful. They follow actually from totally standard considerations of colimits and limits in spaces. And I want to pose this as an exercise. So what might be useful is to refer again to our videos in the higher algebra section on limits and colimits. There were some tricks there for limits and colimits in spaces that might be useful here. So this of course only applies if you have the trivial action. In general, you should think of homotopy orbits as doing some kind of derived quotienting. So there are lemmas like if you take a space, like an actual simplicial set with an actual action by a simplicial group, if it happens to act freely, then the homotopy orbits are represented by the actual quotient. And if it's not free, for example, as you see here, if it's trivial, then it kind of gets blown up in a certain way. So now I've hinted at the fact that an action by S1 will appear. And what's the relation to Hochschild homology? So to get a glimpse of that, we have the following statement about S1 actions in the infinity category dz. So it turns out the infinity category of functors from BS1 to dz is equivalent to the category of modules in dz over the algebra A, which appeared in our discussion of Hochschild homology already. Namely, A was simply an exterior algebra on a degree 1 element, epsilon. So this is a graded algebra. You can turn it into a DGA by taking the zero differential, and then that gives you an E1 algebra, in fact, even an E infinity algebra, since this is graded commutative. In dz, you can take modules over it, and we claim that's actually the same as just objects with an S1 action. And let me sketch how to prove that. So what goes into that is that functors out of BS1, so giving an S1 action in the sense we previously saw, is actually equivalent to a category of modules over the DGA, so over the E1 algebra you get in DZ from chains on S1. So that uses a little argument, for example, that you have some adjunction between DZ and spaces, and that this has some favorable properties. I won't go into that part of the argument, but I want to tell you about how to compare this chains of S1 guy to A. So, of course, the homology of this DGA is just this graded algebra, but that doesn't necessarily mean that there's actually an equivalence between them, say, like a quasi-isomorphism of DGAs or something like that. Right? If you ignore the multiplicative structure, then there's some general results that tells you that every chain complex is quasi-isomorphic to its homology with the zero differential, at least over the integers. In general, if you put some extra algebraic structure on it, this is what's called a formality question. So this doesn't work in general. But we claim in this case it does. And the trick here is that we have maps from the free E1 algebra on a degree 1 generator, which I'll also call epsilon, both to this guy C star S1 and to this guy A. And in both cases, we want to just send E on to the element, to a cycle representing the generator of degree 1 homology. All right, so this is a free E1 algebra in this category DZ. And now it turns out one can work out what the homology groups of this guy are. And in degree 0 and degree 1, these maps are already isomorphisms on homology. So the degree 1 homology of this free E1 algebra is just generated by this guy epsilon. And then in higher degrees, you get more stuff, but the higher degrees just don't matter. Both of these maps factor through maps from tau smaller equal 1 of this free E1 guy. And these maps now are equivalences, right? What this tau smaller equal 1 does is it kills the higher homology groups of a complex. And so this guy just has H0 and H1 given by Z in both degrees, and these maps are isomorphism on homologies, right? But it turns out these are multiplicative, since this tau smaller equal 1 functor is lax monoidal on dz bigger equals 0. So that's a little argument that appears quite often, is that if you take connective guys, then of course the truncation of their tensor product is not necessarily the same as the tensor product of the truncations, right? The latter is usually not truncated, but it's true that this construction is lax monoidal, lax symmetric monoidal even. So in particular, this guy inherits from this algebra an E1 algebra structure, and since these maps were multiplicative, these are 2. So this gives you a zigzag of equivalences between them, so they're equivalent as algebras. Right. And in fact, we haven't used all that much about knowing the higher homology groups, right? So it turns out you can do the same for any En. still works, the argument still works the same. So these are even equivalent as E-infinity algebras, but of course we haven't even stated here that this C star S1 is an E-infinity algebra. For example, that does come from the fact that S1 is like a commutative topological group, but let me not go into that. But these guys are equivalent even as E-infinity algebras, if you say it correctly. All right, so this finishes the proof sketch. And here's one remark I want to make, because this looks like somehow these perspectives are completely interchangeable. But it turns out this equivalence is not compatible with monoidal structures. So there are obvious monoidal structures on both sides. Here we have just the pointwise monoidal structure, right? If you take two functors, you can just tensor them together in the target. That gives you a monoidal structure. And here, when we defined HC minus and HP, this like periodic Hochschild homology and so on, we used on this A Hopf algebra structure, where this epsilon was primitive. It went to epsilon tensor 1 plus 1 tensor epsilon. I guess in that context we called it B actually. I'm sorry about switching up the notation. It corresponded to the con operator, and the monoidal structure was built in such a way that the con operator is a derivation. So it turns out these two very natural choices of monoidal structures don't match up under this equivalence. And that comes from the fact, if you trace it back through what goes wrong here, that comes from the fact that these monoidal structures correspond to Hopf algebra structures on these algebras A and C star S1. And this argument we gave here does not allow us to identify the co-multiplications. So there one has to be very careful. We will later define generalizations of HP and HC minus using S1 actions instead of the con operator, as we did it for ordinary Hochschild homology. And there it will turn out that working with the monoidal structure you get on that side works in full generality. But it turns out that even though this monoidal structure is not quite the right one on the infinity categorical level, on homology of these things, of HP, of HC minus, and so on, you get the same product structure. So this doesn't invalidate what we did for computations for HP and HC minus back when we did this in a more elementary way, but one has to be a little careful. Right, and maybe it's actually compatible with the monoidal structure using a difficult argument, but certainly not with the symmetric monoidal structures. Okay. So, similarly to how we constructed an action of such an exterior algebra on Hochschild homology, our goal today will be to construct the analog, namely an S1 action, on Hochschild homology in an arbitrary infinity category. So here's the main theorem that we will be discussing, which is that on Hochschild homology of an E1 algebra in some symmetric monoidal infinity category C, we have a natural S1 action. And of course that means something like that the functor HH refines to a functor that goes from E1 algebras in C to not just C, but functors from BS1 to C, objects with an S1 action, such that if you forget down to C, if you pass through the underlying object, you get back our original HH functor. And as a little addendum, this agrees with the other S1 action on Hochschild homology relative to the integers obtained from the con operator. Right, the con operator defined an action by an exterior algebra like this, and through this proposition that gives you an S1 action. And so if we generalize that, then this better be true. So we will discuss the construction for the general S1 action today. I'll not talk about how to compare this to the con operator, but I'll put a nice paper that proves that in the video description. All right. So in order to get this S1 action on Hochschild homology, we will want to put additional structure on the cyclic bar complex, right? We constructed this as a simplicial object. We will find today that we can put an even more structured index category instead of delta op beneath this. And so that will naturally lead to this S1 action. So this involves what's called the cyclic category due to con. So we will define a kind of precursor of that now, called the paracyclic category. So this is the paracyclic category, denoted lambda infinity. And this is a one category with objects given by totally ordered sets with Z action, so through monotonous, through order preserving maps, which are equivalent as totally ordered sets with Z action to sets I'm going to denote 1 over n times Z. And of course, as a totally ordered set, this is just equivalent to Z. But this indicates that the Z action is by translation by, well, 1. So if you would identify this with Z, then it would correspond to the ordered set Z with Z action by translation by multiples of n. And that might become confusing very quick because you have multiple Z's here. So we will just denote this 1 over n times Z. Right, but all of these look like Z. The only thing that differs is how far a generator of Z shifts under this action. And morphisms are the obvious ones. So morphisms are equivariant order preserving maps. So, and now the key fact that we have for this lambda infinity is that it comes with some extra structure. Namely, we have an S1 or BZ action on lambda infinity, right? So I will switch to calling this just S1 very soon, because it's a little confusing that this BZ still has kind of another E1 structure left. Of course, this comes from the fact that the Z even had an E infinity structure. But we will also see BS1 appear and so on. So let me switch to calling this S1 very soon. But it turns out for this, it's actually very nice that we can write this as BZ. Namely, how do we get this action? Well, on the level of just one categories, we can completely explicitly give away this BZ acts on lambda infinity. And this is just done by the map BZ cross lambda infinity to lambda infinity, which I have to tell you how it acts on objects and on morphisms. And on objects, it's simply, well, the point cross the objects of lambda infinity to the objects of lambda infinity, simply the obvious map. So on objects, we just act in the trivial way. So somehow this is just an action on the level of morphisms. What do we do there? Well, on morphisms, we have Z acting on hom lambda infinity 1 over nz, 1 over mz, right? This is how my objects look generally, to the same hom simply by translation. So simply by using that, we have this z action on this object 1 over mz, right? It's just translating by 1. So I have this kind of action, and that defines me an action of this monoidal category Bz on lambda infinity. And then after taking nerves, this defines me an object, an action of the equivalent Kahn complex S1 on lambda infinity, on the nerve of lambda infinity. And so this was the paracyclic category. We now also define the cyclic category. As the following one category. So the objects are the same as for lambda infinity, and morphisms are given by hom in lambda from 1 over nz, 1 over mz is hom in lambda infinity between these guys modulo this z action. So we just identify morphisms that differ just by a shift like that. So in some sense, we've simply taken the quotient of this lambda infinity by that action. And the crucial property of this construction, why is this a good thing to do? The crucial property is that on the level of infinity categories, if you pass to the nerve of lambda and the nerve of lambda infinity, then this really exhibits lambda as the homotopy orbits of your BZ or S1 action on lambda infinity. Right? This is not automatic. You can, of course, check that if you form this kind of colimit in one categories, that this gives you this one category lambda. There you really just perform the necessary identifications on the level of morphisms, since on the level of objects you're not doing anything. But this is a stronger statement, because generally one categories considered as a full subcategory of infinity categories are not closed under colimits. A diagram of one category might become not a one category, might get higher morphisms. So this is kind of crucial. And of course, it's related to the fact that the Z action here was actually free. So this is out of the same, like out of the general vicinity of this fact that I told you about earlier, that somehow if you have a group, a space with a free action by some simplicial group, that then homotopy orbits are really just computed by the actual quotient. So I will not prove this, but that's the idea, that somehow here you're taking a quotient by a free action. So what this tells you is that now if we look at functors out of this category, that you have the following property. If you take functors out of this nerve of lambda into any infinity category C, then that's the same as an object in the following, namely functors from lambda infinity to C, and then homotopy fixed points under the S1 action, right? We have an S1 action on lambda infinity. You can put the trivial S1 action on C, and then you get an induced S1 action on the functor category. And you can, of course, take the limit over BS1. And you should simply read this as saying that giving a functor out of this cyclic category is the same as giving a functor out of the paracyclic category, which is S1 equivariant with respect to the trivial action on C. But of course, an S1, like being S1 equivariant in this infinity categorical world is more than just a property, it's a structure. So this won't be a full subcategory on the functor category without the HS1 here. Right. So what's going on here? Well, this is almost the universal property of this colimit statement. The only problem is that somehow the functor category is not the mapping space, right? The universal property of limits and colimits talks about mapping spaces. This is a statement about the functor category, but there's this general trick that allows you to reduce to that statement. So how does this go? Well, if we want to show that this limit here, right, this is a limit over BS1, that this agrees with that, then we just check the universal property. So we take the mapping space from some arbitrary infinity category D into the left-hand side. And we want to show that this has the universal property of that limit. So what does that mean? Well, it just means that this should be the limit of maps into the diagram. So in that case, just into functors from nerve lambda infinity to C, and then taking the limit outside, which in this case is still just a limit over BS1. So let's just write this as homotopy fixed points. Okay, that's what the universal property of this statement means. And now, the mapping space in cut infinity is, if you remember that, it's the maximal Kahn complex in the functor category, right? So map between two infinity categories is you take fun, the full functor category, and then you throw away all non-invertible morphisms and corresponding higher simplices. And now for fun, you have these kinds of exponential laws, right? Here we have functors into some functor category, so we can kind of switch things around. And then since we take the maximal Kahn complex at the very end on the outside, we still have these exponential laws, right? So this is what we want to show. but it's equivalent to the corresponding statement where we take the nerve of lambda mapping into fun dc. And here we take the nerve of lambda infinity mapping into fun dc, and then homotopy fixed points on the outside. Okay, but this is now really just the universal property of this colimit, right? It's just saying that the space of maps out of the colimit is the same as the limit over the space of maps out of the individual parts of the diagram. It's a very general trick, and just as a little teaser, you'll need that for an exercise that comes later. All right, so in terms of the cyclic category, we can now make the following definition, namely, similar to simplicial objects, we have cyclic objects. So cyclic object in infinity category C is a functor from the nerve of lambda up to C. And this is not just simplicial, this is not just kind of similar to simplicial objects, it's actually related. Namely, in the following way, we have a functor from the category delta to lambda infinity. And this takes the totally ordered set n minus 1, so I'm writing n minus 1 because that's the one with exactly n elements, 0 to n minus 1. It takes that to the set z cross n minus 1 with the lexicographic order, where lexicographic simply means that if you compare two pairs, you first compare with the first coordinate, and then if they're equal, you compare with the second coordinate as kind of a tiebreaker. This is lexicographic because that's how things in the lexicon are sorted. And another way to think about this, of course, is that this simply is looking like a long disjoint union of these totally ordered sets, ordered from left to right. And the z action is by the first coordinate. So this is also the same as 1 over nz, right? Just as an ordered set, this looks like z, and the z action just shifts n steps further. Note the indexing shift here. All right, so we have this functor, and the underlying simplicial object of a cyclic object is obtained via the following composition. We can restrict from this lambda up further to lambda infinity up, right? This is simply just, if you think about lambda as a quotient of lambda infinity, then this is simply restricting along that quotient. In terms of the colimit description we just proved, where we said that functors out of lambda are the same as equivariant functors out of lambda infinity. This is just forgetting that you had an equivariant functor. And then from here we can further forget by restricting along this to delta op. That gives you a simplicial object. Right? And so you should think of these cyclic objects as kind of simplicial objects with some extra structure. And so one question we can ask here is, if we have a simplicial set, we like to take its geometric realization. What happens if we start with a cyclic object? What do we know about its geometric realization? And the first thing is that instead of taking the colimit over delta op all the way to the right here, we can also take the colimit over this delta op infinity here in the middle. And it turns out that actually gives the same thing. So the lemma here is the diagram where we take a functor on delta op and we form its colimit, or we restrict down to, sorry, this was lambda infinity op. We can also restrict down to delta op and then take its colimit. So the difference here is whether we take the colimit over lambda infinity op or delta op. Well, this commutes. And of course, if you state it like this, then you're also, you're using already that somehow you can make factorial choices for colimits and so on. But there's a kind of hands-down way of expressing the same fact, which is that the functor from delta op to lambda infinity op has a certain property called cofinality. So there's a certain class of functors which just have the property that restricting along them doesn't change what the colimit of any diagram is. And the claim is that this functor is such a cofinal functor, the functor from delta up to lambda infinity. And it turns out that that's something you can check by explicit combinatorics through something called Quillen's theorem A. We'll not do that here, but it's kind of fun. You have to prove that certain things are contractible, like certain simplicial sets are weakly contractible. We'll just use this, and we'll use it in the following way. So if we have a cyclic object, then we might be interested in the geometric realization of the underlying simplicial object. But what this tells us is that we can equally well just take the colimit over just the restriction to lambda op infinity. And this lambda op infinity, it has this z action floating around and so on, this s1 action floating around and so on. So this might be promising. So what do we have here? Well, this is the other lemma that we need, which is that for a cyclic object x, so this is a functor from lambda op to c, the colim over lambda op infinity, so but which actually, I mean, of course this means the colimit of the restricted functor, but should be clear, which is by this comment the same as taking the colimit over delta op. This naturally carries an S1 action. And the proof is simply this fun composition. We start with fun nerve lambda op c. Right? That's where our cyclic object lives in. And now we could just restrict to this guy, but remember the lemma we proved earlier shows us that this is actually equivalent to taking such an equivariant functor out of lambda op. which we encoded in this category, which was given by homotopy fixed points on this functor category, right? So it actually gives us a point in there and not just in the bare functor category. And now we can take the co-limit. Sorry, I should have taken nerves over here as well. I guess I've been a little sloppy with nerves, but so we can take the co-limit of functors here that gets us into C, and one can take co-limits in a factorial fashion. So you actually get somehow, right, you had this S1 action on this category. The co-limit takes you to C with the trivial S1 action. And now if you take the limit over BS1, what you get here is you get an induced map, like an induced functor between the homotopy fixed points with respect to S1 on this category with interesting S1 action to the category C with just trivial S1 action. So you should think of this as simply the functor colim under or inside of HS1, right? We've just taken the functor, or I guess natural transformation in cut infinity called colim. It goes from this guy to that guy, and then we've just applied HS1. And now, what is this? Well, remember when we did spaces, we said that if you take a space with a trivial S1 action and you take homotopy fixed points, that simply maps from BS1 into your space. We're doing something similar here. We're taking a category, an infinity category, and we take the trivial S1 action on it, and we take the limit. And I claim this is still simply factors from BS1 to C. And I want to pose this as another exercise. So this amounts to checking that this guy really has the universal property of this limit. So you want to map some category in there and then do a similar trick to what I did earlier when we showed that this, when we discussed this homotopy fixed point description over here in an earlier lemma. So I'll leave that as an exercise, but with that, the proof is complete, right? We've gone from here, a cyclic object, to here, which, like, this is the category of cyclic objects, this is the category of objects with S1 action, and we've simply produced a functor between them. And of course, the underlying object you just get by just forgetting the HS1 here, passing through the underlying objects here. So in particular, this underlying object is really the co-limit over lambda infinity, which we showed is the same as the co-limit over delta op. So now we have this very nice combinatorial kind of extension of simplicial objects, these cyclic objects, and we've seen their geometric realization automatically carries an S1 action. So all that's left to do is to produce such a thing, right? So the claim, of course, is that the cyclic bar complex is actually a cyclic object, hence the name. And this is all we need to prove the theorem that I stated earlier, that Hochschild homology always has a natural S1 action. So this is, strictly speaking, the theorem minus this statement about compatibility with the Kohn operator. So in order to remember, the cyclic bar complex came from this functor from delta op to this category associative tensor active that had to do with associative algebras. So we will just extend that functor to lambda, thereby giving a structure of a cyclic object. So here's a fun, explicit combinatorial way of doing this. We let cut Z denote the following functor from this paracyclic category, contravariant functor from the paracyclic category to associative tensor active. You remember this was totally ordered finite sets with maps between them. No, sorry, this was not totally ordered finite sets. Sorry, this was just finite sets. So there's one object for every natural number, but then the maps between them were not just maps of finite sets, they had this additional structure where we fix for every object in the codomain, in the target, and a total ordering on the set of its pre-images. A little subtle. So in here we take, so what does this functor do? Well, it takes an object S, remember this is one of these 1 over nz, to the set of Z equivariant cuts. And what do I mean by a Z equivariant cut? Well, here's a pictorial way of thinking about it. If you think of your S as simply this infinite totally ordered set, infinite in both directions, and you have this Z action on it, let's say it shifts everything by 3 to the right, but it could be some other number, then by a Z equivariant cut, I just mean one choice of placing cutting positions between these dots in such a way that these form a single orbit under the Z action. So for example, for this guy, where the Z action shifts by 3, there are 3 different choices I could make. There's this choice, and there's the choice that's 1 to the right. I hope the colors are okay, otherwise just look at the order which I'm drawing these in. So these are orange. And then the third choice is, well, the remaining positions, 1 more to the right. So, of course, what this means is that such a cut simply consists of a partition of S into subsets S minus 1, S0, S1, and so on, such that each of these is smaller than the next one, and these are disjoint and they cover everything, and the Z action simply sends one bijectively onto the next. Right? That's another way to phrase this, but the important fact here is that we consider the equivariant cut given by this and the equivariant cut where we've simply shifted the indexing the same, right? So the indexing is not part of this. So that's why there's only finitely many ones. Somehow if you've shifted your original cut here 3 positions to the right, then the picture looks the same. So there's only n such guys. This is precisely an n element set if we evaluate it on this 1 over nz. Okay, so that's what we do here. And again, this is contravariantly functorial, because of course if you have a map between 2 objects in here, you can just take the pre-image, and that's still such an equivariant cut. So this is a contravariant functor, and what's the pre-image? Right, we need to turn this not into just a functor to finite sets, but into this funny category, associative tensor active. So we need to discuss pre-images. So what's the pre-image of such a cut? in cut ZS. So that's going to lie in cut ZT under the induced map F star for some map from S to T. And of course, that's consisting of all cuts between the images Fs0, Fs1. So this is very similar to what we did back when we defined this cut sig, like the simplicial diagram for the cyclic bar complex. So if you're confused by this, check out that video where we defined Hochschild homology in infinity categories. We're doing a very similar construction here. Okay, so these pre-images always consist of all the cuts in between two subsets, or I guess translations of that. So here you have finitely many choices, and they're kind of canonically ordered from left to right. Right? You just choose two adjacent subsets of these SIs, and then you look at their images, and there's finitely many cutting positions between them. You just order those left to right. And so this naturally comes with the structure of the functor to this associative tensor active. And since we consider sort of a cut and its translation by the Z action as the same thing, you see that this functor is Z invariant on morphisms, right? So induced maps are invariant under this Z action. So it factors through a functor from lambda to a associative tensor active. So here's a cyclic object. And all we need now is that the underlying simplicial object is actually the cyclic bar complex, as we promised. Right? So the cyclic bar complex was given by this cut sig. And so what we claim here is that the restriction to delta op is precisely cut sig, the functor from associative tensor active. Right? This was sending a totally ordered set, one of these bracket n guys, to the set of all the ways to cut that into two pieces, where we identify the two trivial ways, where one of the sets is empty. We identify those to one element. So I claim that it's basically obvious if you've digested the definitions. So I will leave this as an exercise for you to really digest this construction and the corresponding construction of this cut sig. Right, and that finishes what we set out to do, right? So this tells us that the co-limit of the cyclic bar construction of an E1 algebra carries an S1 action, because the cyclic bar construction just refines to a cyclic diagram and not just a simplicial diagram. All right, that does it for today. Hope to see you next time.